At this moment, space itself is stretching at 700,000 miles per hour. The universe is expanding faster than the speed of light. Every second, the universe is growing more than anyone could ever imagine. But still, the universe continues to swell toward the infinite void that no one can ever reach. We are chasing cosmic mysteries, such mysteries that will shatter everything you thought you knew. Discover why every point in the universe thinks of itself as the center of reality. Witness the invisible force that makes up 70% of existence but that we can never see. And confront the frightening mathematics that predicts the inevitable last breath of our universe. If you think your mind is ready to be completely turned upside down, press the like button. If you are ready, we are starting. Section 1. The expansion of space. Itself, the cosmic truth that turns our minds upside down. At this moment, space is expanding at 700,000 miles per hour and is pushing galaxies away from us faster than the speed of light. In every second you spend on Earth, even while you are just blinking your eye, a region of space that we know is 1 million light-years wide expands by about 22 meters. Understanding how our universe is really expanding will turn upside down everything you know. Because the universe is not expanding into nothing. But the truly shocking thing you will experience when you learn how space itself is moving. Space is not empty, it is a moving stage. You think space is empty, don't you? It is such a vast place that most of us think a place this huge must be nothingness. Wrong. Space is a three-dimensional platform where physics is staged. It can bend near massive objects, vibrate with gravitational waves, and most astonishing of all, it can grow. The intergalactic voids are stretching like an invisible rubber. The distance to the nearest star is increasing a little bit every second. Space is expanding and carrying everything along with it. Even while you are watching this video, every atom in your body is expanding together with space, though by amounts so tiny we cannot notice. This cosmic truth challenges everything our minds don't want to accept. When you blow up a balloon, the balloon expands into the room around it. The room provides the necessary space for the balloon to grow, and right at that moment you realize our universe is completely different from this. How does the universe expand within itself? The universe contains all existing space. It is not expanding into anything. Outside the universe, the word place remains a completely meaningless word. Imagine this. You are living on the surface of a balloon and you do not have the ability to see up and down. Your entire reality exists on that curved surface. As someone blows up the balloon, every point on the surface moves away from every other point. From your perspective, space itself is growing. In your two-dimensional world, there is no outside into which it can expand. Now add one dimension. We live in three-dimensional space, and space is expanding just like that balloon surface. And of course, even the phone in your hand is slowly expanding together with space. Even the distance between us and the moon is increasing because the universe is expanding. But we do not feel this because the difference is we cannot perceive dimensions beyond our three. Space grows within itself, and as it grows, it creates more space. Scientists call this internal expansion. Expansion happens everywhere at the same time. Cosmic expansion also happens between your atoms, but the electromagnetic forces holding your body together are 1 trillion times stronger than the force of expansion. Things were starting to make sense But then inside our galaxy, even interstellar distances are bound by gravity and keep the stars tied together. But between galaxy clusters separated by millions of light years, nothing can stop the ruthless growth of space. The numbers blow our minds. Every second, a region of space 1 million light years wide grows by about 22 meters. That means galaxies, millions of light years away, are fleeing from us at hundreds of thousands of miles per hour. Not because they are moving through space, but because space is carrying them along. Edwin Hubble's cosmic discovery. In 1929, Edwin Hubble thought he would find a calm and still universe. Instead, he faced cosmic chaos. Every galaxy he studied was moving away from our Milky Way like fleeing refugees. That night, Hubble did not know he was going to see with his own eyes a discovery that would shake the world of physics. But after that night, the world of physics was never the same again. The faster they were running, the farther away they lived. This discovery shattered the scientific worldview. Even Einstein had assumed the universe stayed forever constant and unchanging. What would you have done? When his own equations predicted expansion, Einstein added a mathematical correction factor and tried to keep everything static. Later, he described this as my greatest mistake. Hubble, using the cosmic fingerprint technique, measured galaxy speeds. Every element in the universe, when heated, produces light at certain colors. Hydrogen glows red at a precise wavelength. Helium shines yellow at an exact frequency. These cosmic signatures never change, but Hubble discovered something impossible. The familiar hydrogen and helium signatures were stretched toward the red end of the spectrum. The farther away a galaxy stood, the more its light was shifted to red. Redshift, the signature of cosmic expansion. This redshift revealed that galaxies were fleeing from us at tremendous speeds. Mathematics was telling an incredible story. Galaxy 2 million light years away was moving at about 45 ms. A galaxy 4 million light years away was fleeing at 90 ms. Double the distance, double the speed. This relation was valid everywhere Hubble looked. Hubble realized this discovery was not just local, it was valid for the whole universe. He named it the Hubble law. It states that the recession speed is equal to the distance multiplied by a number called the Hubble constant. Today we know this constant is about 70 kilometers per megaparsec. In simpler terms, for every 3.25 million light years of distance, galaxies flee 43 miles faster per second. The implications stunned astronomers. If everything is moving away from everything, then long ago everything must have been much closer. Track the expansion backward in time, and all matter in the universe is squeezed into an infinitely small point. This backward calculation led to the Big Bang theory. Hubble's discovery meant our universe has an age. Space itself began expanding 13.8 billion years ago from a state unimaginably hot and dense. Before that moment, neither space nor time existed in the way we understand them. Cosmic expansion explains why the night sky looks dark. If the universe were infinite, eternal, and static, then every direction you looked should have been blazing with starlight. Section 2, Hubble's discovery and cosmic redshift, the key that opens the secrets of the universe. Galaxies are escaping from Earth at impossible speeds, but the truly shocking thing was that Edwin Hubble, while thinking in 1929 that he would find a calm and static universe, faced cosmic chaos. Every galaxy he looked at was behaving like refugees escaping from our Milky Way. The faster they were running, the farther away they lived. This discovery shook the scientific worldview from its foundation. Even Einstein had assumed that the universe remained forever constant and unchanging. From the results of his own mathematical equations, he foresaw expansion, and he was so surprised by this finding that he added a mathematical patch. Einstein did not know this at that time, but in later years Einstein would call this one of the greatest mistakes of his life. Cosmic fingerprint, the secret language of galaxies. Hubble used a revolutionary technique to measure galaxy speeds, cosmic fingerprint analysis. Every element in the universe, when heated, produces light at certain colors. Hydrogen shines red at a definite wavelength. Helium glows yellow at an exact frequency. These cosmic signatures never change anywhere in the universe. Just as every human being on Earth has a unique fingerprint, every element also had its own unique fingerprint. And right at that moment, Hubble encountered something impossible. The familiar hydrogen and helium spectrum lines were not where expected, but had shifted toward the red end of the spectrum. The farther away a galaxy was, the more its light had shifted to red. This red shift revealed that galaxies were moving away from us at tremendous speeds. The redshift phenomenon is one of the strongest pieces of evidence of cosmic expansion. That night, Hubble had only fixed his eyes on space to measure galaxy speed, but what he found was not only this, he also discovered that the universe itself had an age. Hubble's law, the universal expansion rule. Hubble's mathematical calculations revealed an incredible story. A galaxy 2 million light-years away was moving at about 45 miles a second. A galaxy 4 million light-years away was escaping at 90 miles a second. Double the distance, double the speed. This relation was valid everywhere Hubble studied. He gave it the name Hubble's law. The recession speed is equal to the distance multiplied by the Hubble constant. Today we know this constant is about 70 kilometers second per megaparsec. If you did not understand the word megaparsec, you can think like this. For every 3.25 million light-years of distance, galaxies are moving away from us 43 miles faster per second. Things were beginning to make sense, but the effects completely astonished astronomers. If everything is moving away from everything, then long ago everything must have been much closer. Follow the expansion backward in time and all matter in the universe is squeezed into an infinitely small point. The birth of the Big Bang theory. This backward calculation laid the foundations of the Big Bang theory. Hubble's discovery meant that our universe had an age. Space itself began expanding 13.8 billion years ago from a state unimaginably hot and dense. Before that moment, neither space nor time had an existence in the way we understand, because we thought that before the Big Bang there was no time. Thus, since there could not be the concept of before, everything was meaningless. That is, everything seemed like nothingness. Cosmic expansion also explains why the night sky looks dark. If the universe were infinite, eternal, and static, then every direction you looked should have been shining with starlight. Instead, most of the universe remains invisible because the light coming from distant regions has not yet had enough time to reach us. Cosmological redshift versus Doppler effect. If it were you, which explanation would you prefer? There could be two different causes of redshift. The first, galaxies moving inside space, Doppler effect. The second, the expansion of space itself, cosmological redshift. The Doppler effect is similar to the change of sound when an ambulance passes by you. While the source moves toward you, the frequency increases, blue shift. While it moves away, it decreases, redshift. Cosmological redshift is completely different. Galaxies are not moving too much inside space. While space itself expands, it stretches light waves like a rubber band. The reason why our galaxy reddens, although it does not move, is the expansion of the path light travels. That is, because space expands, The path of light stretches like a rubber band, and this was causing the light to redden until light comes out of a galaxy and reaches us. It travels for billions of years. During this period, the continuous expansion of space pulls back the light waves. Blue light becomes green, green light becomes red, red light turns into infrared waves. Verification of modern observations. Modern telescopes confirmed Hubble's findings with incredible precision. The James Webb Space Telescope measured galaxy distances with better than 2% accuracy. Every observation supports the shocking truth that our universe is expanding mercilessly. But what is even more disturbing is that the most distant observable galaxies of the universe are escaping faster than the speed of light. Galaxies farther than about 14 billion light-years are moving away from us at speeds that even light itself cannot reach. So much so that they are going beyond the horizon, which we can never reach, by exceeding the universal speed limit. The Hubble constant problem. The crisis of modern cosmology. And right now, we are faced with one of the biggest crises in the history of cosmology. Two completely independent Hubble constant measurement methods give results that differ by 9%. This 9% difference may seem insignificant. It is not. Both measurement techniques achieve better than 2% precision. The mismatch exceeds the error margin of both methods by far. There is a fundamental mistake in our understanding of cosmic expansion. The first method examines the cosmic microwave background radiation, the echo of the Big Bang. This ancient light carries detailed information about how the universe looked when it was only 380,000 years old. Cosmologists, by analyzing the small temperature fluctuations in this primordial glow, can calculate how fast the universe is expanding today. This technique gives a value of about 67 km/s per megaparsec. The second method measures the distances to nearby galaxies using Cepheid variable stars. These stellar beacons change their brightness in regular periods, and this period is directly related to their absolute brightness. This local measurement technique produces a value of about 73 kms per megaparsec. Search for a solution and the future. This Hubble tension means the shaking of the basic framework of our cosmology. Either the cosmic microwave background measurement is wrong, or the local measurement is faulty, or there is an important physics missing in our standard model. Nobel laureate Adam Rees leads the team doing the local measurements. His group has developed their techniques for decades, checked for systematic errors, and increased their precision. Consistently, they find the value 73. The James Webb Space Telescope had the potential to solve this debate definitively. Instead, Webb confirmed the measurements that break our understanding of the universe. The telescope's unique precision and sensitivity eliminated systemic errors in previous observations and confirmed the local expansion rate measurements. Even the James Webb Space Telescope, the most powerful telescope we have, instead of solving this cosmic crisis, deepened it further. Section 3. The absence of a center and every observer. Feeling at the center, the cosmic illusion. Stand anywhere in the universe and look around you. Every distant galaxy appears to be fleeing from your position in every direction. You feel as if you are sitting at the very center of cosmic expansion. Move to another galaxy and repeat the observation. From that new position too, every distant galaxy scatters in all directions. That galaxy also appears at the center of expansion, but the truly shocking thing is that this cosmic illusion arises from the nature of uniform space expansion. Since the expansion affects all regions equally, every observer sees identical patterns of recession speeds. You can think of it this way: there are billions of planets in the universe, and each planet thinks it is in the very middle of the universe. How is it possible that everyone thinks they are at the center of the universe? The balloon analogy. two-dimensional universe model. Take a deflated balloon and draw dots on its surface with a marker. Name each dot as a different galaxy. Now, while watching your cosmic map, slowly inflate the balloon. As the rubber stretches, each dot moves away from every other dot. The magic happens when you focus on any single dot. Choose the dot you named the Milky Way. From the perspective of this galaxy, all other dots are fleeing in every direction. The Andromeda dot is moving away. The Centaurus dot, since it started farther away, is fleeing faster. Every galaxy seems to be escaping from the central point you selected. If you inflated the balloon, you could see that each dot is receding equally. And right at that moment, shift your attention to the Andromeda dot. From this new perspective, every other galaxy flees from Andromeda in all directions. The Milky Way dot moves away. The Centaurus dot, because of its large distance, is still fleeing faster. Now Andromeda appears to be sitting at the center of cosmic expansion. This balloon shows why Hubble's law works the same way from every position. The expansion of space creates a situation where every observer sees themselves at the center of the universe. There is no preferred position, no special cosmic address. Every galaxy experiences identical patterns of expansion. The mathematics of expansion without a center. The balloon analogy also reveals another important truth. The galaxies themselves are not moving inside space. As the balloon material stretches, it carries the dots along with it. Similarly, space itself is expanding and carrying the galaxies on the cosmic journey. Galaxies remain relatively stationary in their local pieces of space, while space grows around them. This explains how galaxies can appear faster than the speed of light without violating Einstein's speed limit. A galaxy continues to expand very slowly, but that is not the only effect. The expansion of space itself intervenes, and this creates incredible recession speeds. The speed of light limitation applies to motion inside space. It does not limit how fast space itself can grow. When space expands fast enough, it can carry distant galaxies away from us at superluminal speeds. Think of a galaxy 15 billion light-years away. The space between us and this distant galaxy expands in such a way that it pulls the galaxy back at about 1.5 times the speed of light. The galaxy itself moves very slowly in its local space, but the expansion of the intervening space creates an incredible recession speed. The non-central nature of the Big Bang. The Big Bang did not happen at a specific place in space. Instead, it happened everywhere at the same time. The initial singularity was not a point in space, but a moment when all of space was squeezed into zero dimension. As the expansion began, every point in space equally joined the growth. There was no central location of the cosmic explosion. This concept challenges our daily intuitions about explosions and expansion. When a bomb explodes, debris flies from the central explosion toward the surrounding empty space. Cosmic expansion works completely differently. Space itself grows, carrying matter along with it. There is no surrounding empty space into which the universe can expand because the universe contains all existing space, the evidence of the cosmic microwave background. The non-central nature of expansion explains why we can see the cosmic microwave background radiation from all directions. This ancient light was emitted when the universe became transparent 380,000 years after the Big Bang. We observe this radiation as coming from every direction because every point in space participated in that cosmic transparency moment. If expansion had a center, we would expect to see the cosmic microwave background concentrated in only the one direction from which expansion originated. Instead, the radiation fills the sky with extraordinary uniformity and confirms that expansion affects all regions equally without any preference for position or direction. The effects of future expansion. Because there is no center or edge, acceleration affects the entire universe uniformly. Dark energy increases the rate of expansion everywhere at the same time, pushing all galaxies away from all other galaxies with increasing speeds. This universal acceleration leads to unsettling predictions about the ultimate fate of everything that exists. And right now, we are facing the fact that cosmic expansion will eventually spread all energy into infinite space and leave the universe forever cold, dark, and lifeless. Billions of years from now, when we look at the sky, we will be able to see only a few faint stars because all the other stars will have expanded far beyond the cosmic horizon. Section 4. Galaxies racing beyond light. Speed picture. This mind-bending reality. Right now, as you read these words, countless galaxies hurtle away from us at speeds that shatter Einstein's cosmic speed limit. The James Webb Space Telescope has detected galaxies fleeing at velocities exceeding 186,000 miles per second. Yet Einstein's relativity remains unbroken. How can this impossible contradiction exist? The answer reveals the most counterintuitive truth about our expanding universe. These distant galaxies don't actually move through space faster than light. Instead, space itself carries them along like passengers on a cosmic conveyor belt that operates beyond all speed restrictions. This fundamental distinction between motion through space and motion with space changes everything we thought we knew about cosmic boundaries. Consider the interstellar object 3I Atlas, the mysterious comet that visited our solar system. Even this alien visitor, traveling at tremendous speeds relative to our Sun, crawls like a snail compared to the recession velocities of distant galaxies. While 3I Atlas moves through space at roughly 100,000 miles per hour, galaxies 14 billion light-years away recede from us at nearly 300,000 miles per second, 3 times faster than light itself can travel. But here's where your understanding of physics gets completely inverted. Einstein's special theory of relativity prohibits any object from accelerating past light speed through space. This cosmic speed limit remains absolutely inviolable. Nothing with mass can reach 670 million miles per hour relative to its local surroundings. Every experiment ever conducted confirms this fundamental law of nature. Yet Einstein never restricted how fast space itself could grow. When the universe expands, it creates more space between objects without moving the objects through space. Imagine 2 ants walking slowly across an inflating balloon. Each ant crawls at a leisurely pace across the rubber surface. However, as the balloon inflates, the distance between them increases much faster than either ant can walk. This balloon analogy captures exactly how cosmic expansion works. Galaxies drift slowly through their local patches of space, typically at speeds of just a few hundred miles per second. Meanwhile, space itself expands around them, carrying them apart at velocities that can exceed light speed for sufficiently distant objects. The galaxies never violate Einstein's speed limit because they barely move through space at all. The mathematics reveal the exact distance of this cosmic horizon. Any galaxy farther than approximately 14 billion light-years recedes faster than daylight. Scientists call this boundary the Hubble horizon. Beyond this cosmic prison wall, galaxies become fundamentally unobservable. They exist, but we can never detect their light or communicate with them. Their signals travel toward us at light speed, but space expansion carries them away faster than their light can approach. Think about what this means for a moment. Somewhere beyond this invisible barrier, civilizations might have developed technologies that dwarf our wildest imagination. They could have solved the mysteries of dark energy, mastered interstellar travel, or discovered physics beyond our current theories. Yet we will never know they exist. The expanding universe has placed them forever beyond our reach. Even more disturbing, galaxies we can see today will eventually disappear beyond this horizon. As expansion accelerates, more and more galaxies will cross the boundary between observable and unobservable. In the far future, our descendants will see a much emptier universe as distant galaxies vanish from view one by one, like ships disappearing. Beyond Earth's horizon, the C-2025 N1 Atlas interstellar comet provides a stark contrast to these cosmic recession speeds. This alien visitor from beyond our solar system represents the fastest natural object we can directly observe, yet it moves at a crawl compared to distant galaxies carried by expanding space. The comet's journey from interstellar space to our cosmic neighborhood took millions of years, while space expansion carries distant matter across equivalent distances in mere moments of cosmic time. The superluminal recession of distant galaxies affects the light we do receive from closer objects. Consider photons emitted by a galaxy 8 billion light-years away. When this light began its journey toward us 8 billion years ago, the galaxy was much closer. Expansion has since carried it to a much greater distance. During its 8 billion-year journey, this ancient light traveled through continuously expanding space. The expansion stretches the light waves themselves, increasing their wavelength and reducing their energy. Blue light becomes green, green light becomes red, red light becomes infrared. This stretching effect increases with distance, making the most distant observable galaxies appear extremely red. Astronomers call this phenomenon cosmological redshift, and it provides direct evidence for the ongoing expansion of space itself. The James Webb Space Telescope has revolutionized our ability to observe these superluminal galaxies by detecting their incredibly redshifted light in infrared wavelengths. What began as ultraviolet radiation from distant galaxies arrives at Earth as infrared radiation after traveling through billions of years of expanding space. Without Webb's infrared vision, these cosmic refugees would remain completely invisible to us. This creates a fundamental paradox in our understanding of cosmic communication. While galaxies beyond the Hubble horizon recede faster than light, information cannot travel between them at any speed. The cosmic horizon represents an absolute boundary for knowledge itself. No matter how advanced our technology becomes, we can never learn what lies beyond this expanding prison of space. But here's what makes this even more unsettling. The horizon itself grows larger every second, yet the number of observable galaxies actually decreases over time. While the boundary expands outward at light speed, cosmic acceleration carries distant matter away faster than the horizon can grow. We're losing cosmic information faster than we can gain it. Are you beginning to grasp the terrifying implications? The universe is not just expanding, it's actively erasing its own history. Section 5, the universe's baby photo and the Big Bang. Imagine holding a photograph of the universe when it was just 380,000 years old, a cosmic infant compared to its current age of 13.8 billion years. This ancient snapshot exists, and you can detect it right now with nothing more than an old television set. Turn to an unused channel, and roughly 1% of that static represents the afterglow of creation itself, the cosmic microwave background. Radiation. But here's what will shatter your understanding of cosmic origins. This baby photo reveals that space expansion began from conditions so extreme that physics itself breaks down. The James Webb Space Telescope has pushed our observations deeper into cosmic history than ever before. Yet even this technological marvel cannot penetrate the opaque wall of the early universe. What it has discovered instead challenges everything we thought we knew about how space and time began. 80,000 years after the Big Bang, the cosmos flashed like a cosmic camera bulb. For the first time since creation began, space became transparent to light. Before this moment, the universe remained completely opaque. hotter than the surface of the Sun and filled with a plasma so dense that photons could barely travel the distance of an atom before being scattered in random directions. Picture trying to see through the interior of a star. That's what the early universe was like everywhere, simultaneously. Free electrons bounced light around like cosmic pinball, making the universe as opaque as thick fog. No structure could form, no clear images could exist, no information could travel freely through space. The cosmos was essentially blind to itself. Then cosmic expansion worked its magic. As space grew larger, temperatures dropped. At exactly 3,000 degrees Fahrenheit, still hot enough to melt copper, electrons suddenly combined with atomic nuclei for the first time in cosmic history. In an instant that astronomers call recombination, the cosmic fog lifted. Space became transparent and light could finally travel freely across the universe. This moment created what scientists call the surface of last scattering. Just as we can only see the surface of the Sun because light from deeper layers gets scattered before reaching us, we can only observe the universe back to this moment of cosmic transparency. Everything beyond this ancient surface remains hidden, behind an impenetrable wall of opacity. The light emitted during this cosmic dawn has traveled through space for 13.4 billion years to reach us today. Expansion has stretched these primordial photons from visible wavelengths into microwave radiation, with a temperature of just 2.7 degrees above absolute zero. This cosmic microwave background now bathes every cubic inch of the universe in faint radio waves, the stretched echo of creation itself. When radio astronomers first detected this radiation in 1965, they initially thought it was interference. From pigeon droppings on their antenna, they had actually discovered the most important evidence for the Big Bang theory. This ancient light proves that the universe began in an incredibly hot, dense state and has been expanding and cooling ever since. But the cosmic microwave background reveals something even more mysterious. Its temperature appears remarkably uniform across the entire sky, varying by less than 1 part in 100,000. This presents a fundamental puzzle. Regions of space separated by billions of light years show identical temperatures, yet they could never have communicated with each other at the speed of light. How can opposite sides of the observable universe have the same temperature if they were never in contact? The answer requires us to confront the most violent expansion in cosmic history, a period so brief and extreme that it challenges our understanding of reality itself. During the first fraction of a second after the Big Bang, space underwent cosmic inflation, an exponential expansion that dwarfs anything we observe today. In less than a trillionth of a trillionth of a trillionth of a second, the universe expanded by a factor larger than the number of atoms in the observable universe. This incredible stretching took tiny regions that were in thermal equilibrium and carried them to cosmic distances faster than light could travel between them. Think about what this means. The regions we observe on opposite sides of the cosmic microwave background were once close enough to share the same temperature. Inflation then stretched them apart so rapidly that they appear disconnected today, yet they retain their identical properties from before the expansion began. It's like taking a small patch of uniform fabric and stretching it until it covers a football stadium. Every part remembers its original properties. The James Webb Space Telescope has provided unprecedented detail of this ancient radiation, confirming the standard model of cosmology while simultaneously deepening certain mysteries. The tiny temperature fluctuations Webb observes in the cosmic microwave background represent the seeds of all cosmic structure. Slightly warmer regions contain slightly more matter, and over millions of years, gravity amplified these tiny differences into the galaxies and galaxy clusters we see today. These primordial fluctuations originated from quantum uncertainty itself. During inflation, quantum fluctuations smaller than subatomic particles were stretched to astronomical scales, becoming the blueprint for cosmic architecture. Without these quantum seeds, the universe would be perfectly smooth and uniform. No galaxies, no stars, no planets, and certainly no interstellar visitors like 3I Atlas could ever have formed. But here's what makes this cosmic baby photo truly unsettling. It represents our absolute limit of direct observation. We can never see beyond the moment when space became transparent. The universe's first 380,000 years remain forever hidden behind the wall of cosmic opacity. Everything about the Big Bang itself must be inferred from its consequences rather than direct observation. What happened during those missing first moments? The mathematics suggest conditions so extreme they defy comprehension. All the matter and energy that would eventually form trillions of galaxies was compressed into a region smaller than a proton. Temperatures reached 100 million trillion degrees, hot enough to break apart the fundamental forces that govern reality. Even more disturbing, the Big Bang wasn't an explosion in space, it was the explosive creation of space itself. There was no center where the explosion occurred because there was no space for a center to exist in. Every point in the universe participated equally in this moment of cosmic birth. The expansion we observe today is the continuation of this primordial stretching of space-time itself. The cosmic microwave background also reveals precise values for fundamental cosmic parameters. The universe appears geometrically flat to within 1% accuracy. Dark matter comprises exactly 26.8% of cosmic density. Dark energy accounts for 68.3%. These measurements provide the foundation for our understanding of cosmic expansion and its ultimate fate. Yet this ancient light carries disturbing implications about our cosmic future. If the patterns we observe are correct, the universe will continue expanding and cooling until it reaches maximum entropy, a state where no further change can occur and cosmic death becomes inevitable. Section 6. Dark energy, the force that defies gravity. In 1998, two teams of astronomers made a discovery that shattered the foundations of physics forever. They expected to find cosmic expansion slowing down, gradually overcome by the gravitational pull of all matter in the universe. Instead, they discovered something that defied every prediction. Expansion was speeding up. This revelation introduced humanity to the most mysterious force in existence, dark energy. The evidence came from studying ancient stellar explosions called Type Ia supernovae. These cosmic bombs explode with nearly identical brightness, making them perfect distance markers across the cosmos. When astronomers measured how far away these supernovae appeared versus how fast they were receding, they expected to see a predictable relationship matching standard expansion models. But here's what made their blood run cold. Distant supernovae appeared dimmer than expected. This meant they were farther away than simple expansion calculations predicted. Something had accelerated cosmic expansion, carrying these ancient galaxies to greater distances than anticipated. The universe wasn't just expanding, it was accelerating into an unknown future. Scientists named this mysterious phenomenon dark energy, a term that reflects our complete ignorance about its nature. We cannot see it, touch it, or detect it directly through any known instrument. Yet this invisible force dominates the entire universe, accounting for approximately 68% of all energy in existence. Think about that staggering fact for a moment. More than 2/3 of reality consists of something we cannot understand or observe. The James Webb Space Telescope has provided unprecedented precision in measuring this cosmic acceleration. By observing the most distant galaxies ever detected, Webb confirms that dark energy has been driving expansion for billions of years. These observations show that cosmic expansion began decelerating after the Big Bang, then mysteriously switched to acceleration about 5 billion years ago, roughly when our solar system was forming. What could possibly overpower the gravitational attraction of trillions of galaxies? Dark energy exhibits properties that seem to violate our intuition about how energy behaves. Unlike ordinary matter that dilutes as space expands, dark energy maintains constant density throughout the cosmos. Double the volume of space, and you double the total amount of dark energy. This apparent violation of energy conservation challenges our fundamental understanding of physics. Consider the cosmic inventory. Count every star in every galaxy. Add all planets, moons, asteroids, and interstellar gas. Include every black hole, neutron star, and exotic object astronomers have discovered. This entire collection of ordinary matter represents less than 5% of what actually exists. The remaining 95% consists of dark energy and dark matter, substances, that interact with our reality only through gravitational effects. Dark energy presents the greater mystery. Unlike dark matter, which at least clumps together and helps form cosmic structures, dark energy appears perfectly uniform throughout space. It shows no variation from one region to another, doesn't cluster around galaxies, and doesn't accumulate in dense clouds. Instead, it fills every cubic inch of space with identical density, creating a cosmic force field that pushes space apart. The energy density of dark energy seems insignificant at first glance. Each cubic yard of empty space contains dark energy equivalent to about 6 hydrogen atoms worth of mass. Yet when you multiply this tiny density by the vast volume of the observable universe, dark energy's total influence exceeds all visible matter by more than 10 times. The universe runs on energy we cannot detect or comprehend. Scientists have proposed several theoretical candidates for dark energy. The leading hypothesis suggests it represents the energy of empty space itself, arising from quantum mechanical effects. Quantum physics predicts that seemingly empty space seethes with virtual particles that pop into existence and disappear faster than light can cross an atomic nucleus. This quantum foam might create constant energy density throughout space. However, quantum calculations predict a dark energy density that exceeds observations by a factor of 10, followed by 120 zeros. This represents the worst prediction in the history of physics, off by more than the number of atoms in the observable universe. Either quantum mechanics fundamentally misunderstands empty space, or dark energy has a completely different origin that we haven't discovered. Alternative theories propose that dark energy emerges from extra dimensions beyond the 3 spatial dimensions we perceive. In these models, gravity leaks into higher dimensions on cosmic scales, creating apparent acceleration without requiring mysterious energy fields. Other proposals suggest dark energy changes over time, growing stronger or weaker as the universe evolves. Recent observations from the Dark Energy Spectroscopic Instrument hint that dark energy might indeed be evolving rather than remaining constant. If confirmed, this discovery would require completely new physics to explain how and why this cosmic force changes over time. The implications could revolutionize our understanding not just of cosmic expansion, but of the fundamental nature of space and time themselves. The selective influence of dark energy creates a bizarre cosmic landscape. Within galaxy clusters where matter density remains high, gravity still dominates and holds structures together. But in the vast empty regions between clusters, dark energy reigns supreme, accelerating expansion at ever-increasing rates. This creates a universe of gravitationally bound islands floating in an ocean of accelerating space. Even the trajectory of interstellar objects like Atlas and C2025 N1 Atlas remains unaffected by dark energy on such small scales. These alien comets follow paths determined purely by gravitational interactions with stars and planets. Dark energy only becomes significant across distances of hundreds of millions of light-years, where its cumulative effects overcome local gravitational binding. The dominance of dark energy means that ordinary matter, including everything that makes up stars, planets, and living beings, plays only a minor role in the universe's ultimate fate. We are constructed from the rare 5% of reality that we can actually observe and understand. Our entire visible cosmos, including billions of galaxies and countless stars, represents a tiny minority component in a universe controlled by invisible forces. This cosmic composition creates a humbling perspective on humanity's place in existence. We consist of minority particles in a cosmos dominated by phenomena we cannot detect, measure, or comprehend. Every atom in your body, every star in the night sky, every galaxy Webb observes represents cosmic afterthoughts in a reality governed by dark energy. Future civilizations will inhabit an increasingly lonely universe as dark energy acceleration carries distant galaxies beyond observable horizons. One by one, the lights in the cosmic sky will fade as expansion carries them into unreachable realms. Our descendants will witness the universe becoming apparently empty, with no way to know that trillions of galaxies once filled their ancestral skies. But dark energy raises even more disturbing questions about cosmic acceleration. If this mysterious force continues strengthening, it could eventually overpower all other interactions in the universe, leading to a catastrophic end where space expansion tears apart every structure that has ever existed. What happens when the force that drives galaxies apart becomes strong enough to overcome the forces that hold atoms together? Section 7, Dark Matter, the universe's invisible scaffolding. While dark energy pushes the cosmos apart, an equally mysterious substance holds it together. Dark matter outweighs everything you can see, touch, or interact with by more than 5 to 1. This invisible scaffolding shapes cosmic expansion by creating the gravitational framework upon which galaxies form, yet it remains completely transparent to light and impossible to detect directly through any known method. The evidence for dark matter's existence comes from cosmic architecture itself. Galaxies spin too fast. Galaxy clusters move in ways that defy the gravitational pull of their visible matter. The cosmic microwave background shows temperature patterns that require 5 times more matter than we can observe. Something massive and invisible sculpts the universe's structure, but it interacts with ordinary matter only through gravity's gentle touch. Fritz Zwicky first discovered this cosmic mystery in 1933 while studying the Coma Galaxy cluster. He calculated how much matter the cluster should contain based on its galaxy's orbital velocities. The answer shocked him. The cluster needed 10 times more mass than he could observe to prevent its galaxies from flying apart. Zwicky called this missing component dark matter, launching one of astronomy's greatest detective stories. The James Webb Space Telescope has provided unprecedented views of how dark matter shapes cosmic evolution by observing the most distant galaxies ever. Detected, Webb reveals that dark matter was already organizing cosmic structure when the universe was less than 1 billion years old. These ancient galaxies appear clustered in patterns that match dark matter's invisible architecture, confirming its crucial role throughout cosmic history. But here's what makes dark matter truly alien. It passes through ordinary matter as if nothing exists. Right now, billions of dark matter particles stream through your body every second without any interaction whatsoever. They pass through Earth's entire mass as easily as light passes through empty space. This ghostly matter fills the universe yet remains completely undetectable except through its gravitational influence on cosmic expansion. computer simulations reveal dark matter's intricate cosmic web, vast filaments stretching across hundreds of millions of light-years, connected by dense nodes where galaxy clusters form. This invisible architecture determines where ordinary matter can accumulate and where cosmic expansion dominates. In regions with high dark matter density, gravity slows expansion enough to allow gas clouds to collapse and form stars. In regions with low dark matter density, expansion proceeds too rapidly for any significant structure formation. The cosmic microwave background provides a detailed map of dark matter's distribution when the universe was only 380,000 years old. Tiny temperature fluctuations in this ancient radiation reveal where dark matter had already begun concentrating, creating the gravitational seeds for all future cosmic structure. These primordial variations grew over billions of years as dark matter's gravity attracted ordinary matter into increasingly complex patterns. Think about the implications. Every galaxy, including our own Milky Way, sits within a massive halo of dark matter extending far beyond its visible boundaries. This invisible halo contains roughly 10 times more mass than all the stars, planets, and gas we can observe. The dark matter halo shapes our galaxy's rotation, influences star formation rates, and determines how cosmic expansion affects our local cosmic neighborhood. Interstellar visitors like 3I Atlas and C2025 N1 Atlas provide indirect evidence of dark matter's influence. These alien comets follow trajectories shaped by the gravitational fields of stars and planets, but their paths also respond to the dark matter distribution throughout our galactic region. While we cannot detect dark matter directly, we can map its presence by studying how it affects the motion of objects we can observe. Dark matter particles remain completely mysterious despite decades of intensive searches. They cannot be ordinary atoms because atomic matter would create detectable signatures in cosmic observations that we don't see. They cannot be photons because light doesn't clump together gravitationally. Dark matter must consist of unknown particles that interact only through gravity, the weakest of nature's fundamental forces. Leading theoretical candidates include exotic particles predicted by extensions to the standard model of physics. Weakly interacting, massive particles, WIMPs, could have exactly the right properties to form dark matter. These hypothetical particles would be produced in the early universe but interact so weakly with ordinary matter that they remain undetectable except through gravitational effects on cosmic expansion. Alternative proposals suggest dark matter consists of primordial black holes formed during the universe's first moments, sterile neutrinos that barely interact with anything, or axions emerging from quantum field fluctuations. Each possibility requires different physics and would affect cosmic expansion in subtly different ways. The true nature of dark matter could revolutionize our understanding of fundamental physics. Underground laboratories around the world search for dark matter particles using increasingly sensitive detectors. These experiments attempt to catch dark matter particles in the act of colliding with atomic nuclei, but so far, all searches have come up empty. The particles either interact too weakly to detect, or dark matter has properties we haven't yet imagined. The Large Hadron Collider tries to create dark matter particles by smashing protons together at enormous energies, recreating conditions similar to the early universe when dark matter was first produced. These experiments could potentially solve the dark matter mystery by manufacturing these invisible particles in laboratory conditions where we can study their properties directly. But here's what makes the search even more challenging. Dark matter might not consist of particles at all. Some theories propose that our understanding of gravity itself is incomplete. Modified gravity theories suggest that gravitational forces behave differently on cosmic scales than Einstein's general relativity predicts. creating apparent dark matter effects without requiring invisible particles. The relationship between dark matter and cosmic expansion creates a fundamental tension in modern cosmology. Dark matter tries to build larger structures through gravitational attraction, while dark energy prevents this by accelerating expansion. As cosmic expansion accelerates, dark energy will eventually overcome dark matter's gravitational influence completely, ending all future structure formation. In the distant future, dark energy's dominance will make dark matter's scaffolding irrelevant. No new cosmic structures will form as expansion accelerates beyond the point where gravity can collect matter together. The dark matter web that shaped billions of years of cosmic evolution will become a frozen relic in an exponentially expanding universe. Current galaxy surveys use gravitational lensing effects to map dark matter's distribution across cosmic time. When light from distant galaxies passes through regions of high dark matter density, the invisible matter's gravity bends the light like a cosmic lens. These distortions reveal dark matter's influence on cosmic expansion at different epochs throughout the universe's history. The patterns confirm that dark matter clustering has remained essential for structure formation since the earliest cosmic epochs. Without dark matter's gravitational scaffolding, the universe would be remarkably smooth and uniform. No galaxies, stars, or planets could have formed in a cosmos dominated purely by ordinary matter and dark energy. Yet despite its crucial role in cosmic architecture, dark matter represents just one component in a cosmic inventory that defies human comprehension. Combined with dark energy, these invisible components account for 95% of everything that exists. We live in a universe where the familiar matter that forms our bodies, our world, and everything we can directly observe represents just a tiny minority of total reality. This cosmic composition raises profound questions about the nature of existence itself. Are we truly significant in a universe dominated by substances we cannot see or understand? What does it mean to seek knowledge about reality when the vast majority of that reality remains forever hidden from our senses and instruments? The answers may depend on measurements so precise they challenge the very foundations of cosmic knowledge itself. Section 8. The Hubble Tension. When precision becomes crisis, the crisis began with precision. As telescopes improved and measurements became more accurate, astronomers expected their calculations of cosmic expansion to converge on a single definitive answer. Instead, they discovered a disturbing discrepancy that threatens the foundation of modern cosmology. Two completely independent methods for measuring the Hubble constant disagree by 9%, a difference that could shatter our understanding of cosmic expansion. This 9% disagreement might seem trivial to casual observers, but it represents a catastrophic failure in cosmological physics. Both measurement techniques achieve precision better than 2%. The disagreement far exceeds the margin of error for either method. Something fundamental is wrong with our understanding of how space expands, and the implications extend far beyond academic curiosity. The first method studies the cosmic microwave background radiation, that ancient afterglow of creation we explored earlier. This primordial light carries detailed information about the universe when it was only 380,000 years old. By analyzing microscopic temperature fluctuations in this cosmic baby photo, cosmologists can calculate how fast the universe expands today. The Planck satellite mission, using this technique, yields a Hubble constant of approximately 67 kilometers per second per megaparsec. The second method measures distances to nearby galaxies using pulsating stars called Cepheid variables. These stellar lighthouses change brightness in regular cycles that directly relate to their absolute luminosity. By comparing their apparent brightness to their known luminosity, astronomers can calculate precise distances across cosmic space. The James Webb Space Telescope has revolutionized this approach, confirming local expansion measurements with unprecedented accuracy. Adam Rees, who won the Nobel Prize for discovering dark energy acceleration, leads the team making these local measurements. His group has refined their techniques over decades, checking systematically for errors and improving precision with each observation. They consistently find a Hubble constant of approximately 73 kilometers per second per megaparsec, significantly higher than early universe predictions. Think about what this discrepancy means. If the cosmic microwave background measurement is correct, then nearby galaxies should appear closer than they actually do when we observe them directly. If the local measurement is correct, then our models of the early universe contain fundamental flaws. Either way, our understanding of cosmic expansion harbors a critical error that could invalidate decades of cosmological research. The James Webb Space Telescope entered this controversy with the potential to resolve the Hubble tension definitively. Its unprecedented infrared vision can penetrate cosmic dust clouds that blocked previous observations, revealing Cepheid variables with clarity never before achieved. Webb can observe these pulsating distance markers in galaxies up to 130 million light-years away, providing the largest sample of cosmic distance measurements ever assembled. But here's what makes the mystery even more unsettling. Webb's observations have made the Hubble tension worse, not better. The most powerful telescope ever constructed validates the local measurements that contradict our cosmological models. Webb's infrared capabilities confirm that nearby universe expansion rates exceed early universe predictions by a margin that cannot be explained by measurement errors or systematic biases. Webb's data comes from studying over 300 Cepheid variables across multiple nearby galaxies, cross-checked with carbon-rich stars and surface brightness fluctuations. Multiple independent techniques all converge on the same disturbing conclusion. The local expansion rate significantly exceeds what our best cosmological models predict based on early universe observations. This confirmation forces astronomers to confront uncomfortable possibilities about cosmic expansion itself. Perhaps dark energy has not remained constant throughout cosmic history. Maybe unknown particles influenced expansion during the universe's first billion years. Some theories propose that space itself has properties we have never discovered, creating expansion behaviors that change over cosmic time. Recent observations hint that the solution might involve early dark energy, a hypothetical force that influenced cosmic expansion during the universe's youth before disappearing from the cosmic energy budget. This temporary acceleration could explain why early universe models predict different expansion rates than we observe in our local cosmic neighborhood. Alternative theories suggest that our understanding of gravity itself requires modification. Perhaps Einstein's general relativity breaks down on cosmic scales, creating apparent discrepancies in expansion measurements. Modified gravity theories could explain the Hubble tension without requiring mysterious new forms of energy or exotic particle physics. The stakes of resolving this tension extend throughout cosmology. The Hubble constant determines the age of the universe, distances to galaxies, and the ultimate fate of cosmic expansion. If we cannot measure this fundamental parameter correctly, our entire cosmological framework becomes questionable. Every calculation about cosmic history, structure formation, and future evolution depends on getting the expansion rate right. Some researchers have proposed that systematic errors contaminate one or both measurement methods. Perhaps interstellar dust affects distance measurements in ways we don't fully understand. Maybe the cosmic microwave background analysis makes incorrect assumptions about early universe physics. Independent verification studies have largely ruled out these possibilities, deepening the mystery rather than resolving it. The tension also affects practical astronomy beyond fundamental cosmology. Precise distance measurements depend on accurate knowledge of the expansion rate. The Hubble discrepancy introduces uncertainty into calculations of supernova luminosities, galaxy distances, and the three-dimensional structure of cosmic space. This uncertainty propagates through numerous astronomical studies, affecting our understanding of everything from stellar evolution to dark energy behavior. Even interstellar objects like 3I Atlas and C2025 N1 Atlas indirectly relate to this. Cosmic crisis. These alien visitors provide independent checks on our understanding of gravitational physics within the solar system. If our models of gravity and motion prove accurate on small scales but fail on cosmic scales, this could point toward solutions to the Hubble tension that involve modified physics rather than measurement errors. The resolution may require observations that transcend electromagnetic radiation entirely. Gravitational wave detectors like LIGO could potentially provide independent measurements of cosmic distances through observations of merging black holes and neutron stars. These gravitational standard candles might resolve the Hubble tension by offering a third, completely different approach to measuring cosmic expansion. Future space missions, specifically designed to address the Hubble tension, are already in development. The Nancy Grace Roman Space Telescope will observe thousands of supernovae with unprecedented precision, while the Euclid mission will map cosmic expansion across billions of years of cosmic history. These observations could finally determine whether the tension results from systematic errors or new physics. But what if the Hubble tension cannot be resolved through better measurements? What if it points toward fundamental gaps in our understanding of reality itself? The discrepancy might indicate that cosmic expansion operates through mechanisms we have never imagined, involving physics beyond our current theories. The possibility that our cosmological models are fundamentally incomplete raises disturbing questions about the nature of scientific knowledge. How can we claim to understand the universe's expansion when our most precise measurements contradict each other? What does it mean to build theories about cosmic evolution when we cannot agree on the basic rate at which space grows? These questions become even more urgent when we consider that the Hubble tension might just be the beginning of a larger crisis in cosmology. As our measurements become more precise, we may discover additional discrepancies that challenge our understanding of cosmic expansion in ways we cannot yet imagine. The universe appears to be expanding at different rates depending on how we measure. It's suggesting that space itself harbors secrets we are only beginning to glimpse. Section 9, the universe's ultimate fate. 3 paths to oblivion. The mathematics of cosmic expansion predict 3 possible endings for everything that has ever existed or ever will exist. Each scenario leads to the complete obliteration of all structure, all information, and all possibility of future development. The universe that gave birth to galaxies, stars, planets, and consciousness itself marches inexorably toward one of. These cosmic death sentences and current observations suggest the most unsettling outcome of all. Heat death represents the most likely scenario based on our understanding of dark energy behavior. In this future, cosmic expansion continues accelerating forever, spreading all matter and energy across infinite space until the universe reaches maximum entropy. Temperature differences disappear, making it impossible for any engine to operate or any work to be performed. The cosmos becomes a perfectly uniform, cold, empty wasteland where nothing interesting can ever happen again. The timeline for this cosmic apocalypse spans periods that dwarf human comprehension. In 100 trillion years, 1,000 times longer than the universe has currently existed, the last star will burn out. Every stellar furnace that has ever illuminated space will exhaust its fuel and fade to darkness. No new stars can form because cosmic expansion will have spread matter too thinly for gravity to collapse gas clouds into stellar nurseries. Even after stellar death, cosmic expansion continues its relentless work. White dwarf stars will cool over hundreds of trillions of years, becoming invisible crystallized matter drifting through infinite space. Neutron stars will take even longer to reach absolute zero, their incredible density allowing them to retain heat for cosmic eons. These stellar corpses will represent the last warm objects in an increasingly frigid universe. Black holes will survive longer than any other structures, but even these gravitational monsters face inevitable doom. Stephen Hawking discovered that black holes slowly evaporate by emitting radiation over unimaginably long timescales. A black hole with our Sun's mass would require more time to evaporate completely than the number represented by 1 followed by 67 zeros years. The largest black holes, containing billions of solar masses, will persist for times so vast that writing the number of years would require more digits than atoms in the observable universe. Yet even these cosmic titans will eventually surrender all their mass to Hawking radiation, leaving behind nothing but elementary particles scattered across infinite space. After the last black hole evaporates, the universe will contain only electrons, positrons, neutrinos, and photons spread across distances so vast they rarely interact. The temperature of space will approach absolute zero as expansion dilutes even the cosmic microwave background radiation to infinitesimally low energy levels. But heat death might not represent the most terrifying possibility. If dark energy grows stronger over time rather than remaining constant, cosmic acceleration could intensify until it overcomes every force that binds matter together. This scenario, called the Big Rip, would tear apart every structure that has ever existed, from galaxy clusters down to individual atoms. Recent observations from the Dark Energy Spectroscopic Instrument suggest that dark energy might indeed be evolving, growing more powerful as cosmic time advances. If this trend continues, the Big Rip could unfold over the next 20 billion years, a cosmic instant compared to heat death's leisurely timeline. The James Webb Space Telescope's precision measurements of distant galaxies provide crucial data about dark energy's historical behavior, potentially revealing whether this catastrophic scenario awaits us. The Big Rip timeline progresses through increasingly violent phases of destruction. First, galaxy clusters would disperse as dark energy overcomes their gravitational binding. Individual galaxies would dissolve next as stars scatter across exponentially expanding space. Then, solar systems would break apart as dark energy grows strong enough to overpower stellar gravity. Finally, planets, molecules, and even atomic nuclei would be torn apart by forces more powerful than the electromagnetic interactions that hold matter together. In the final moments before the Big Rip, space itself would expand so rapidly that light could no longer travel between nearby objects. The observable universe would shrink to microscopic dimensions as expansion carries everything beyond detection range. Even fundamental particles would lose contact with each other in a cosmos expanding faster than the speed of light itself. Alternatively, if dark energy weakens or reverses over cosmic time, expansion could eventually slow down and reverse into contraction. This Big Crunch scenario would see all matter and energy collapse back into the singularity from which it emerged, potentially triggering a new Big Bang cycle. The universe might experience infinite cycles of birth, growth, death, and rebirth in an endless cosmic rhythm. Some theoretical models predict that dark energy oscillates over cosmic time, alternately accelerating and decelerating expansion in eternal cycles. These cyclical universe theories suggest that our current acceleration phase represents just one epoch in an infinite sequence of cosmic expansions and contractions. The universe could be immortal, dying and being reborn countless times throughout infinite time. Current observations favor the heat death scenario, with dark energy remaining approximately constant over cosmic history. This condemns the universe to exponential expansion and gradual cooling until all interesting physics becomes impossible. Yet even within this dreary future, mind-bending events will unfold over cosmic timescales that challenge human comprehension. Quantum mechanics predicts that even in a maximally expanded, cold universe, random fluctuations could occasionally create organized structures purely by chance. Over periods measured in years followed by trillions of digits, quantum uncertainty might spontaneously assemble brief pockets of complexity, perhaps even conscious observers, before they dissolve back into cosmic randomness. These quantum resurrections could theoretically recreate any configuration of matter that has ever existed. Copies of Earth, exact duplicates of every person who has ever lived, and perfect reproductions of entire civilizations might spontaneously emerge from quantum noise, experience brief moments of existence, then vanish back into entropy. In infinite time, even infinitesimally improbable events must occur infinitely often. But the most unsettling aspect of cosmic fate involves the accelerating isolation of surviving structures. As expansion continues accelerating, galaxies currently visible to us will disappear beyond our cosmic horizon one by one. Future civilizations will inhabit increasingly empty universes as distant lights fade into unreachable realms. Our descendants may have no evidence that billions of other galaxies ever existed, trapped in cosmic islands surrounded by exponentially expanding emptiness. This cosmic censorship means that advanced civilizations in the far future will possess less information about the universe than we do today. They will inherit a cosmos that appears nearly empty, with no way to deduce its rich history of galactic abundance. The universe will erase its own past through the mechanism of accelerating expansion. Interstellar objects like 3I, Atlas and C2025 N1 Atlas represent fleeting connections between stellar systems in a universe that grows increasingly isolated. These alien visitors carry information across interstellar distances that will eventually become impossible to traverse. As expansion accelerates, even light cannot bridge the growing gaps between cosmic structures. The choice between cosmic endings depends on measurements we may never be able to make with sufficient precision. The behavior of dark energy over cosmic timescales exceeds our observational capabilities, leaving the universe's ultimate fate shrouded in uncertainty. We can calculate the mathematics of each scenario, but cannot determine which future awaits. Reality itself. Yet regardless of which ending ultimately claims the cosmos, all three scenarios lead to the same fundamental result: the complete elimination of complexity, information, and the possibility for further development. The universe that created stars from hydrogen, planets from stellar debris, and consciousness from organic chemistry will eventually eliminate every trace of its own creative achievements. Does this cosmic pessimism render existence meaningless? Or does the temporary victory of organization over entropy give greater significance to every moment of structured complexity, every instance of conscious experience, every brief triumph of information over chaos? The answer may depend on discoveries yet to be made about the deepest nature of reality itself. Section 10. Beyond Dark Energy, the Radical Baby Universe. Theory: what if everything we thought we knew about cosmic expansion was wrong? What if the mysterious acceleration driving galaxies apart doesn't come from dark energy at all, but from something far more extraordinary, our universe literally devouring countless baby universes in an endless cosmic feast? This isn't science fiction, it's a serious theoretical framework proposed by leading physicists to explain the most perplexing mystery in modern cosmology. While the James Webb Space Telescope continues mapping distant galaxies like 3I Atlas and tracking interstellar objects across our solar system, Theoretical physicists are proposing that our expanding cosmos might be fundamentally different from everything we've imagined. The baby universe. Hypothesis, cosmic cannibalism picture. This mind-bending scenario. Microscopic universes constantly pop into existence throughout space, born from quantum fluctuations smaller than atoms. Our larger universe then absorbs these tiny realities, growing bigger with each cosmic meal. This process appears to us as the accelerating expansion we attribute to dark energy. Jan Ambjørn from the University of Copenhagen pioneered this revolutionary idea. His calculations suggest that baby universe mergers could produce expansion, rates matching our observations more accurately than traditional dark energy models. But here's where it gets really wild. These baby universes exist in dimensions beyond our familiar three-dimensional space. Think of soap bubbles forming in a bathtub. Small bubbles constantly merge with larger ones, making the big bubbles grow. In Ambjørn's theory, our universe represents the largest bubble in an infinite cosmic foam. Baby universes merge with ours like quantum soap bubbles, adding their volume to our expanding space-time. These miniature realities remain completely invisible to us. They interact with our cosmos only through gravitational effects, creating the illusion of mysterious dark energy driving acceleration. The merging process happens continuously throughout space and time, injecting fresh space-time into our universe at rates that perfectly match observed cosmic expansion. The mathematics behind cosmic merger, the equations describing baby universe, absorption work remarkably well. When theoretical physicists calculate the expansion rate that constant universe mergers should produce, the results align with telescope observations better than standard cosmological models. This isn't just mathematical elegance, it's a potential revolution in our understanding of reality itself. Baby universe creation connects directly to quantum mechanics. Virtual particles constantly appear and disappear in empty space, representing quantum energy fluctuations. Under extreme conditions, these fluctuations might spawn actual pocket universes rather than simply vanishing back into the vacuum. Most baby universes start incredibly small, far smaller than protons, but grow rapidly after birth. Some remain microscopic and merge with our universe almost immediately. Others might develop their own physical laws before eventually joining our reality. The merger process creates a steady stream of new space-time that drives the cosmic acceleration we observe. Can you imagine the implications? Every breath you take occurs while our universe literally consumes parallel realities. The space around you grows larger not because of mysterious dark energy, but because microscopic cosmos constantly surrender their existence to expand our own. Quantum foam and dimensional boundaries. The baby universe theory requires extra dimensions, beyond the three spatial dimensions we experience. These higher dimensional spaces provide the nursery, where baby universes form and mature before merging with our reality. We cannot perceive these dimensions directly because our particles and forces remain confined to our three-dimensional membrane floating in higher dimensional space. String theory naturally predicts such extra dimensions and multiple universes. In these models, our familiar particles stay trapped on a three-dimensional surface, while gravity can leak into all dimensions. This dimensional leakage could allow baby universes to communicate gravitationally with our cosmos, even when other interactions remain impossible. The quantum foam concept becomes crucial here. Empty space isn't truly empty, but seethes with virtual particle pairs that pop into existence and annihilate faster than light can cross a proton. Baby universe theory suggests that under special conditions, these quantum fluctuations can evolve into genuine pocket universes instead of disappearing. Picture the fabric of space-time as a cosmic ocean where waves constantly rise and fall. Most waves remain small and quickly subside back into the sea, but occasionally a wave grows large, enough to become a permanent feature of the ocean itself. Baby universes represent quantum waves that escaped their normal fate and evolved into independent realities. Testing the untestable. Observational challenges. Here's the brutal truth about baby universe theory. It might be scientifically untestable. Using current methods, these microscopic cosmos interact with our reality only through gravity, making them essentially undetectable with existing technology. How do you observe something that exists in dimensions you cannot access? Future gravitational wave detectors offer our best hope for finding evidence. The merger of a baby universe with our cosmos should create ripples in space-time similar to black hole collisions. But distinguishing universe merger signals from other cosmic phenomena would require unprecedented sensitivity and sophisticated analysis techniques. The James Webb Space Telescope and other advanced instruments continue mapping cosmic expansion with incredible precision. If baby universe mergers truly drive expansion, their effects might leave subtle signatures in the cosmic microwave background radiation or the distribution of distant galaxies. These cosmic fingerprints could provide indirect evidence for parallel universe absorption. Think about the scientific challenge here. We're proposing that invisible universes from inaccessible dimensions constantly merge with our reality, creating effects we interpret as dark energy. The theory explains observations beautifully, but requires accepting phenomena that may remain forever beyond direct detection. Critics and alternative explanations. Most physicists remain deeply skeptical about baby universe theories. Critics argue that the model simply replaces one mystery with another. Instead of explaining dark energy, it requires undetectable parallel universes with precisely the right properties to mimic dark energy effects. The theory may be mathematically elegant, but lacks the observational foundation that science demands. Alternative explanations for cosmic acceleration continue competing for acceptance. Modified gravity theories suggest that Einstein's general relativity breaks down on cosmic scales, creating apparent acceleration without requiring mysterious substances. Extra-dimensional models propose that gravity behaves differently across vast distances, naturally producing the observed expansion patterns. Phantom dark energy models allow the mysterious force to evolve over time, growing stronger or weaker. As the universe ages, recent observations hint that dark energy might indeed be changing, potentially ruling out constant baby universe merger rates while opening possibilities for more complex interdimensional dynamics. The scientific method requires testable predictions and observable consequences. Baby universe theory faces the fundamental challenge of proposing phenomena that may remain permanently beyond experimental verification. Can a theory be considered scientific if its core predictions cannot be tested? The multiverse connection, infinite realities, baby universe theory connects to an even grander possibility. The multiverse hypothesis suggesting infinite parallel realities constantly influence each other through mechanisms beyond ordinary physics. If our universe regularly absorbs smaller cosmos, it might also interact with peer universes of similar size through dimensional boundaries we cannot perceive. Eternal inflation models predict that cosmic expansion continues forever in most regions of space, creating infinite numbers of pocket universes with different physical properties. Our observed reality might represent just one bubble in an infinite cosmic foam where universes constantly merge, split, and exchange energy through higher dimensional processes. String theory naturally accommodates multiple universes existing on different dimensional membranes. These parallel realities could drift through higher dimensional space like sheets of paper floating in a cosmic wind. When membranes collide or approach each other closely, their gravitational interactions might create the expansion effects we observe. Consider the staggering implications. Every moment of your existence might be influenced by countless parallel versions of reality. The expansion carrying galaxies away from us could result from our universe's ongoing interactions with infinite cosmic siblings we can never directly observe. Philosophical implications, realities true. Nature. If baby universe theory proves correct, it fundamentally changes our understanding of existence itself. Reality becomes far more dynamic and interconnected than we ever imagined. Our universe grows through constant consumption of parallel realities, making cosmic expansion a form of interdimensional metabolism. The theory suggests that nothing in our cosmos truly exists in isolation. Every atom in your body participates in a universe that feeds on alternate realities. The space around you expands because microscopic cosmos sacrifice their existence to fuel our cosmic growth.